Bienvenidos y bienvenidas de nuevo. La siguiente exposición será en inglés. Las personas que requieren audífonos para la traducción lo pueden solicitar. Continuamos esta vez con Martina McGlouglhin, directora del Sistema de Investigación de Biotecnología y Programa de Educación de la Universidad de California de Estados Unidos. Martina es profesora asociada adjunta del Departamento de Fitopatología de la Universidad de California. Tiene un masterado en genética molecular de la University College de Dublín, Irlanda, y un doctorado de la National University de Irlanda en biotecnología. Martina nos presenta en este momento el tema Regulación y Competencia en el mercado de los organismos genéticamente modificados. Martina, bienvenida.
Can you hear me from here? I apologize that my Spanish is non-existent. I could give you a talk in Latin, I'm going to depart a little bit from my prepared slides, and apologies to the interpreter in response to some comments that were made from the last speaker, so please excuse a slight diversion. I think it's very important for us to realize that by 2050 we're going to have 9 billion mouths to feed, and many of those are going to be in less developed countries if we look at the steep climb here in population. Now, to feed that number of people, we're going to need 70% more food. Now, while I wouldn't suggest that biotech is a panacea for all the world's ills, it's a useful set of tools that I think it's important for us to remember that we can use with all of the other tools that we've been using for 10,000 years to genetically modify food crops. Yes, I said we've been genetically modifying food crops for 10,000 years. And we often forget that. We seem to sometimes think we've just invented the art of genetic modification. We haven't. It's just that the modern methods we use, in my opinion, are far more precise, far more predictable, far more controlled than any of the older techniques. We are going to have to produce this food using less water, less fuel, less fertilizer, less pesticides. And without those modern techniques, quite frankly, I don't think we're going to be able to meet the burgeoning population that is about to take over our Earth. If we're to look, and again, apologies to the interpreter, this is a new slide, just to remind us of exactly what we've been doing for the last 100 years to our crop plants. Here is an example of irradiation mutagenesis. We have about 3,000 crops in production today that came from either irradiation or chemical mutagenesis. This is to help nature along. But at the molecular level, we have no clue what we're doing. We're completely potentially messing up the genetic makeup of these plants. Called antherculture. And then you have to use a chemical called coal. You can make them in the lab one day, they can come into commercialization the next. Obviously, it's going to take longer time than that. But because they're not considered genetically modified, they are not regulated. Whereas the biotech crop, where you're using recombinant DNA technology, is one of the most heavily regulated techniques in existence. It takes about 10 years for any plant crop product to come through the deregulation process before it's approved for commercialization. If we're to look at the products that are coming down the line, the vast majority of those that are out there right now, the ones that are in international trade, are in the area of what's called agronomic traits. So this is specific modifications that are being put into our crop plants to allow them to grow with all of the other things that are competing, i.e. all the insects, the diseases, the weeds that are also trying to take over our fields. Well, with biotech, we can use the natural DNA process to actually protect our plants against those pests and diseases. So we can eliminate the need to use chemical pesticides. We're hopefully going to be able to eliminate the need to use chemical fertilizers. As we're looking at issues of climate change, we're hopefully going to be able to develop plants that will be able to adapt very quickly to changing climates. So they will be more drought tolerant, more salt tolerant, more cold tolerant, being able to survive where we have infusions of salt water. You really can't do any of this without taking a biotech approach. Consumers are interested in quality traits. So we are looking, using biotech, to introduce improved nutritional characteristics in our plants, to make them healthier, to turn off all of the negative products that are in our plants, toxins, allergens, for example. We're in the birthplace of the potato here. As you know, potatoes have a toxin called solanine, and using biotech, you can use what's called RNAi to turn off the production of that particular toxin, so you won't have this glycoalkali being produced in the green area that you sometimes find in potatoes. You can use it to turn off allergens in peanuts, so it will be safe for people who are allergic to peanuts to eat peanuts. Well, more specifically, it will be safe for them to be around individuals who are eating peanuts, because those that have anaphylactic shock, it takes a very, very tiny amount of this albumin protein in peanuts to cause this response. With biotech, you can turn off those. You can also increase the shelf life. We lose billions upon billions of dollars every year through wastage in food. With biotech, we can increase the shelf life so we don't have to keep throwing out our bananas after a few days. Likewise, we can use this technology to produce whole novel high-quality nutritional components in crops. For example, we can make perfect proteins. We can make the protein that your body absolutely needs. It has all the essential amino acids in the correct ratios, and we can put this into a crop plant. Obviously, this is going to have to be regulated, because you're going to have to determine the safety of these plants. But we already do this. All over the world, there are extensive regulatory regimens in place to look at the safety for consumers, for animals, and for the environment. And if we look at the actual adoption of these crops, rather interestingly, for the first time ever last year, more biotech crops were produced in less developed countries than in developed countries. So of the 172 million hectares of biotech crops grown in 28 countries, 20 of those countries were less developed countries. And more extraordinary, of the 17 million farmers that grew these crops, 16 million, 90% of those farmers are actually, are actually from less developed countries. So this technology is being adopted wholeheartedly all over the world, and especially in the Americas, as you can see, there is a large degree of adoption of this technology. One area that is notably missing is Europe. There has been, in fact, Europe is going backwards. Countries have pulled out of growing these crop plants, quite frankly, because it is just so difficult to be able to do this within an incredibly restrictive regulatory environment. And in fact, if we look at who have the brighter prospects, and I picked Brazil here because, of course, that is one country where there is a large production of soybeans, biotechnology soybeans. In fact, both Argentina and Brazil, almost 100% of soybeans are now biotech. If we look at the potential going forward, Brazil has a 40% growth rate for production, whereas Europe, the growth is 4% between 2010 and 2019. This is for all crops, this is not just biotech. If you look, this is way too sensitive. If you look at the soybean pipeline, So a lot of the research that's being done and the products that are about to be commercialized are still in the area of what I call biotic stresses, as in resistance against pests and diseases and allowing us to grow these crops with minimum use of herbicides. But there's also quality traits coming down the line, where they're looking at improving the oils in these soybeans. So you have, for example, high oleic oil. This means you can use this to produce French fries, but it has reduced saturated fats, so it is a much healthier oil. It also won't go rancid, or it won't go off when you use it to fry. Another oil that's been introduced are omega-3. You often hear omega-3 fatty acids are very good for you. Well, in fact, one of those, called, apologies to the interpreter, docosahexaenoic acid, makes up 30% of your brain. So if somebody calls you a fathead, it's actually a compliment, because you need this oil to be able for your brain to function. Right now, we're dependent on fatty fish from the oceans, but with biotech, you can actually put this into soybeans. They're also putting it into canola. So the soybean is becoming almost completely modified using modern technology to improve its ability to be grown with minimum amount of chemicals and maximum amount of nutritional characteristics. But if you look from a regulatory perspective, these plants, as I said, are thoroughly regulated. In the US, this is done by the Food and Drug Administration, by USDA APHIS, and by the EPA. And they're looking at all of the potential characteristics that you need to be concerned about from a food safety perspective and from an environmental impact perspective. And over 600 papers, this is 600 peer-reviewed papers worldwide, have determined that these crops are as safe, if not safer, than conventional crops. One of the longest studies was actually done by the European Union, where they had 400 teams looking at 150 research projects back over 25 years. So this is a serious longitudinal study. And they determined that because scientists have a better notion of what they're doing using this technology, and because it's so highly regulated, it probably is safer than any other mode of production. So it is, I think, important to remember that research was done in the EU. And here, the problem, of course, that we're looking at worldwide is each jurisdiction imposes different standards and requirements. We just don't have standardization across the world. And this is a huge impediment to trade, as you can imagine. The other thing, most jurisdictions, including the EU, impose zero tolerance for any presence of any unapproved GMO. So you could have one soybean kernel, just one bean, in 10 trillion beans, and you have to throw away the whole shipment. I'm sorry, but that is utterly ridiculous, especially when there are no safety issues involved. But that's what we're dealing with from a trade perspective at this point in time. And of course, with modern techniques also being developed by biotechnology, our ability to detect these beans is becoming increasingly sensitive. We can pretty much detect anything at this stage. But just because we detect it, should it matter? In my opinion, absolutely not, that it's testing ad absurdum. Some of the wrecks that I see, quite frankly, coming down the line, because we have non-standard definition of GMO, you're going to have non-uniform rules. And in fact, really, if we look at some of the systems that mean the GM itself is bred away, so basically when you cross it, you may lose the gene. Is the initial plant still defined as a GMO? Likewise, if we have a genetically modified rootstock, say for example, we're making resistant wine, we're making grapes that are resistant against specific diseases. As you know, grapes are mostly grafted. So we have a genetically engineered resistant rootstock, we have a non-genetically modified scion that is the particular part that actually makes the wine. The reason we do this, of course, is because the wine industry is very conservative, so we want to make sure that the varietals remain the same. Now, is this whole plant genetically modified? Because clearly you're going to have movement through the plant of various components. How do you define that? If the final product, say if you produce an oil from genetically modified soybeans, no way on earth can you test that oil and say it came from a genetically modified organism, because you don't have any DNA remaining in there, nor do you have any proteins that are produced in the genetically modified plant. So the oil itself cannot be traced. So do you still have to define it as part of a GMO? And the last one, sorry. Transgenic orthologs. Sorry, that's a big word. This means genes that descended from a same common ancestor. Basically what we're calling cisgenics from a same plant. Should you even call these transgenes? Again, in my view, no, you shouldn't. The real issue I think we're focusing on here, we're so concerned about preparing for all risks that we're considering every potential risk except the risk of avoiding all risks, with the results that we'll do nothing. And in fact, to me, I call that a sin of omission. It will mean we'll depend on older, less safe, less stable, less sustainable technologies to produce our crop plants, when we should be looking at what is the best possible tool and technique we can use in any particular instance, whatever that tool is or wherever that's from. If we're looking at new technologies coming down the board, I just mentioned cisgenics there. This is where we're taking genes from one plant, in fact the same species, and introducing them into the same species. Is that a transgene? I'll give you a very specific example, again that's relevant to Ecuador. As you know, that I'm Irish, and the Irish potato famine, so thanks to you for the potatoes, but no thanks to the famine that our dependency on it led to. But the potato famine was caused by a particular fungus-related organism called Phytophthora infestans. It's called late blight disease. Right now we have to spray with fungicides, which are not good to use. There is a wild variety of potato from Mexico that have two resistance genes that confer complete resistance against late blight disease. You can take those genes, put them into potato, get protection, and you do not have to play with fungicides. You do not even have to spray with organically approved copper sulfate. You don't need to use anything. Yet, the company that's developing that's BASF in Europe, they've pulled out of Europe because they're finding it impossible to get through the regulation process. This is a complete disincentive to them, with the result that Europe now has to depend on continuing to spray potatoes with nasty chemical fungicides, or even with the organically approved copper sulfate. Some other technologies that are coming down the line, you're not even going to be able to detect at all whatsoever. This is the technique called genome editing. I'm not going to go into the scientific detail, but using these modern techniques, you can go into the genome, make slight modifications that cannot be detected. These modifications could have occurred naturally to confer novel traits on these crop plants. How do you regulate those if you're never going to be able to detect them? How do you label those? You're not introducing new genes, you're just making minor modification in the crop itself. This is very similar to the old-fashioned irradiation mutagenesis, except you're not screwing up the whole chromosome, you're just making those minor modifications to get the trait you want. And it's really important to remember, as I just said, many of these traditional forms of breeding can produce hazardous crops and foods, but they're not regulated at all. They are generally regarded as safe. They are not required to go through any pre-market approval before they appear on your shelves. Yet all of these techniques that we're looking at from a biotech perspective are probably going to be regulated. The safety focus on to me, distracts from some of the real hazards that are out there where GM can have specific answers. Wow, this keeps jumping, sorry. There are multiple potential areas where we can have trip-ups from a trade perspective. Unnecessarily slow approvals, and this is especially true in Europe. Here, where the EU claimed to get rid of its moratorium back in 2004, and we're looking at actually the length of time where you're going to, the amount of time it takes from an application being submitted to go through the authorization and approval process. And it's extraordinarily long. Then problems come up where you're finding unapproved, for example, here they found unapproved corn variety that was brought in soybeans. So it brought the soybean imports to a complete halt, even though it was not a soybean contaminant. Some places the process is completely broken. It has taken years to go through a process of getting approval for something that has already been approved in the US and has gone through all the safety regulations, all the environmental impact regulations, and yet still sitting on the shelves in Europe. If we look at stacked traits, so remember I showed you the soybean a moment ago, where you have multiple new genes in there for insect resistance, drought tolerance, improved nutrition. Now you're looking at multiple variations if you're going to have to go through approval for every single one of those. Look at the number of permutations if you're looking at 6 traits. We already have 8-way stacked traits. 720 permutations. If you're going to have to approve those one by one, that you're bringing the whole world to a full stop. It's, in my opinion, utterly irrational. And if we look at some of the issues that are going to occur from low-level presence, so remember I told you, if you can test, you can potentially find one soybean in 30 trillion soybeans. If you have asynchronous approval, that is where at least one cultivating country has already authorized the crop, while another, the importing country, and here I'm using the example of Europe, where they have not, that's going to stop everything. And of course with stacked traits, it means some traits will be approved and some won't. But because the lowest common denominator is the one that hasn't been approved, the whole thing is stopped. Likewise, if you have asymmetric approval, that is, the cultivating country has authorized the crop, but its developer isn't looking to get approval in a foreign market. If this shows up on your shipment, again, you're screwed. And of course, you have research events. This is where a country has authorized GE crops for field trials, but have not authorized them for commercialization. If this shows up, again, and it has happened, the whole thing comes to a dead stop. And you have multiple ways for contamination to occur. You can have outcrossing. Mother Nature is infinitely capable of transferring genes. The issue should be, when does it matter? In my opinion, mostly it doesn't matter. Really where we've had the problems, of course, is human nature, where you get commingling and unintentional presence of GM crops. And when you look at this whole combination, many GE products, many countries, slow approval, stacked traits, zero tolerance, we have a trade wreck. And it's just waiting to happen. This is an EU snapshot. And the potato I just talked to you about there, the Fortuna potato, we have foreign approvals, but you don't have, because of asynchronous approvals, you're looking at total sources for potential presence is about 8. If you look at all these crops, and I'm not about to go through them in detail, you're looking at about 42 potential sources for just a few crops where you can pull the whole thing to a stop because of a small, tiny, low-level presence of a transgene. And I just talked to you, it's like this is really bouncing around, just to give you a graphic image of what I was referring to there when I was talking about one soybean. Say it gets into a barge. One barge is 15 rail cars. That goes into 50 large semis. Then you have 380 barges here, sorry, 50 semis, I should be reading it this way, 15 rail cars, one barge, 38 barges into one of these huge big ships. You have 330 trillion soybeans. And if you detect in there one soybean that's transgenic, the whole 330 trillion has to go back. And to me, that is utterly ridiculous. And if you look at the amount of movement of these ships around the world, you can see this is just disaster waiting to happen. And the hard truth is, if you test, and by the way, when I mean if you test the varieties that are out there right now, you are going to find them. Future varieties using these new genome editing tools, non-integrating vectors, you're not going to be able to find them. So maybe the thing is, wait till we get there and this won't be an issue at all. But for now, if you test the existing products, you are going to find them, because 0 is a very small number. In fact, it is not a number, it doesn't exist. And you literally are going to get what you paid for. So what are people doing? They're coming up with workarounds. Compliance, as I mentioned, for GMOs is massive. It costs millions of dollars to go through the process of regulatory approval or in the US deregulation. A huge cost of time, and there's a huge potential liability, as I just showed you, if something shows up that hasn't been approved. The cost of compliance for all of these older technologies I told you about is 0, because they're not regulated, so you don't have to worry about them, even if they're not as safe or as effective or nutritious as modern techniques. So developers are motivated to develop workarounds. They can use what's called marker-assisted selection. That is, you have to go looking for a plant that's compatible, then you can use this biotech technique to be able to select for the specific characteristics you want. But it often takes years to go through the process of integrating the character you want and getting rid of all the characteristics you don't want. The example I gave you of the tomato or the potato that has that are from the deadly nightshade plant, it will take 10 to 15 years to backcross out the characteristics you don't want. With biotech, you could do it in 1 minute by turning off genes. Not even introducing a foreign gene, just turning off a gene that's already in there. And as I mentioned, the non-detectable technologies, these are all coming down the line, and it's only going to be a matter of time before we're using many of those. And as I said, how do you detect them? How do you regulate for that? So we already have problems showing up of biotech crops showing up among non-approved biotech crops. Here in 1999, this was one of the first, GM wheat was found in Thailand. But in fact, the GM was not the wheat, there was corn residue in the wheat. So again, there's no transgenic wheat here, there was corn residue because of the shipping process that they used. Likewise in 2009, GM soybeans in Europe. Again, it wasn't an unapproved GM soybean, it was corn residue again. So you're finding tiny little bits of residue, not even of the same crop, and you're finding the whole thing coming to a halt. One of the ones that was looked into in great detail was linseed flax from Canada. And in fact, after many years of research, they determined that it was false positives. And that's the other thing you're going to find with many of these technologies. Some of the older technologies that are being used for detection, you're ending up with a lot of false positives. And this is possibly what happened with the Roundup Ready wheat that was found in Oregon recently. This brought wheat shipments to Japan to a halt in the US. Now remember I showed you the radiation mutagenesis fields at the start, where you have 80 terabecquerels of irradiation being used to introduce traits. That was from Japan. They use irradiation breeding, chemical breeding, but they are very, very unsure about biotech. And they stopped wheat imports because in one small field that was nowhere near any of the field trials in North America, there appeared to be Roundup Ready wheat. But the test they use has about an 80% false positive rating. Now, subsequent tests showed that in fact that there was some of this wheat in that field, but it was unlikely to be pollen drift or volunteers because it was nowhere near where the field trial was first done. Wheat will not last in the ground for 10 years. So it's likely that there may be mischief here, as in it was deliberately planted. Likewise, Roundup Ready alfalfa, this has been approved, it has been deregulated in the US, but it showed up in the hay of a farmer who never purchased it. They're still trying to figure where that came from, but again, it has brought this alfalfa exports to a stop in the US. So these are real issues that we're dealing with from a trade perspective, but they're not answering, in my opinion, real world questions, like how many lives were saved or environmental damage averted by finding these low-level GM contaminants? None. But there might have been a lot of lives saved if we had approved, for example, golden rice. So golden rice was developed by a Swiss scientist, Dr. Petrikis, and this will protect children, especially from vitamin A deficiency. About 2 million children go blind each year from lack of access to vitamin A. This golden rice provides sufficient amount of vitamin A, it's basically beta-carotene, a precursor, to protect against not only going blind, but development disorders and immune disorders, and yet it is sitting in the Philippines. Most recently, it was actually attacked by vandals, and here you actually can protect against blindness and potential death. But finding these contaminants, all the energy, all the effort, all the money we put into doing that, you are protecting no one. So we are continuing to put funding into the detection of vanishingly smaller amounts of GM contaminants. Where we are not actually doing is looking at ways to protect against real damage to the health and to the environment by all of those products I told you about not being developed. So if I was to ask you, what are these mystery substances? Well, this is bluestone on potato. This is what I grew up with in the west of Ireland. This is approved for organic control, but it has a hazard rating of 1. It's natural, but it's nasty. Whereas with the biotech potato, we have 2 genes that would give complete protection without having to use this. Here we are having malopinin sprayed over vineyards to protect against the glassy winged sharpshooter. Again, at UC Davis, we have vines that have been engineered to protect against this particular disease, but they're sitting on the shelf. Here we have organic apples being sprayed with antibiotics in Switzerland. Again, we have genes that protect these apples against what's called fire blight. Sitting on a shelf, not going through the process of deregulation because it's so costly. Here are 2 particular products. This is the late blight potato. Remember I told you it was a cis gene. Is it really a transgene? It's taken from another potato. Here we have a potato that's protected against acrylamide production. When you cook potatoes, when you make French fries, you produce acrylamide, which is a carcinogen. This is an 80% reduction. There's no foreign genes in there. It is actually innate protection. So are they really transgenes? And here are some crops that are going to completely disappear without biotechnology. Papaya, there is no natural resistance. Only the biotech crop that protects against this virus can protect the papaya plants in Hawaii, and it has already done so. In fact, it's helping organic farmers because it's removing the viral reservoir. Orange juice will completely disappear within 20 years because it's being destroyed by a bacteria called citrus greening. Again, the only way to control it is with biotech genes. These are 2 spinach genes that are protecting it against annihilation. There is no natural or synthetic control system right now. Bananas, they are subject to several fungal, viral, and bacterial disease. Because they're all clones, they're all Cavendish, they are all susceptible, and Cavendish bananas will disappear, I guarantee, within 20 years or so, again, without biotech. And I just mentioned Pierce's disease in grapes. Again, grapes potentially may disappear without taking a biotech approach. So the trade wrecks, in my opinion, will continue if it's assumed that DNA is inherently hazardous. The regulatory trigger is on the process, i.e., we are regulating how you make it instead of regulating the final product. No other product is regulated based on the process that's used to make it. For example, sausages don't have on it that they're produced using extrusion processes. You probably don't want to know how sausages are made anyway. But biotech itself is the trigger. Expectation of zero risk. There is no such thing in life as zero risk. You go outside the door in the morning, you cross the road, there is a risk you're going to be killed. You stay in bed, you develop bed sores, you starve, there is a risk you will die. Life is full of risks. It's how you manage them that's important. Expectation of absolute purity, as I mentioned, that is never going to happen. We really are looking at damages to health and the environment, that these will continue until regulations become science-based and redress real risks, not potential hypothetical risks that have no basis in reality. So with that, I just wanted to show you the number of scientific and medical bodies that are generally positive about biotechnology. And these are the ones that are generally negative. None. All of these international bodies say this technology is safe, it is effective, it is sustainable. And so going forward, just to say what we're looking at technical challenges. We heard this morning there are intellectual property challenges, freedom to operate in developed countries, for example, in developing countries. We're looking at potential liability issues, biosafety, but the biggest concern to me is acceptance. We have to counter all the fear and misinformation that's out there, and we really need to focus on the moral imperative of real need versus hypothetical risk. And thank you, I probably have gone over my time. You're not taking questions now? I think, okay, thank you.